Day 5.
Day 5. All right.
So today we have 2 days more
Yeah. All right. So day 5 here, we want to make a connection here with something that we did in the past, and it's actually something that you guys saw a little bit of, but they set it up nicely for you. Okay, and all you had to do really was plug it into your calculator. Okay, so what we're talking about here is what's known as the binomial probability theorem. Okay, that's what we're going to get to eventually. All right. We're dealing with events that are known as independent events. Okay? Independent events, it's important to understand, are events where the occurrence of one thing happening will have no impact on what happens next. Okay? For example, if I flip a coin and it lands on heads, if I pick that coin up and flip it again, does the fact that I just got a heads matter?
No.
No. The probability of getting a head or a tail is still 50-50. Okay? Those are independent events. They're where the occurrence of one has no impact on the occurrence of the other. Some of them are logical like that, like rolling dice or flipping a coin. Okay? Others are not as obvious. Okay? So, the first thing we want to understand about independent events is the probability of 2 independent events can be found if we're looking for an intersection. The probability of A and B is the probability of A times the probability of B. Okay? So we just said that flipping a coin or rolling a die is independent every time we roll the dice. It doesn't matter what we got the previous time. We have the same probabilities the second time and the third time. Okay? So, if I'm trying to figure out, for example, what's the probability of rolling 2 dice and getting an 8 3 times in a row, let's think about this. Alright? We have roll 1, roll 2, and roll 3. Okay? Does anyone remember what the probability of rolling an 8 is?
I think it's something like, I think it was 4 possibly. It's 1 4.
If you remember, 7 is the most common, and that's 6 out of 36.
It's 5 out of 36?
It's 5 out of 36, yes. 6 and 8 are both 5 out of 36. 5 and 9 are both 4 out of 36, and it just counts down until you get to 2 and 12 are both 1 out of 36. Okay? So, the probability of getting an 8 the first time, we just said, is 5 out of 36. Okay? What's the probability of getting an 8 the second time?
5 out of 36.
5 out of 36. Okay? And the third time it's 5 out of 36. So, using our rule here, the probability of getting an 8 and another 8 and then another 8 is going to be the probability of getting an 8 times the probability of getting an 8 times the probability of getting an 8. Okay? Yes?
Why is 5?
Why is it 5? You remember the table we just saw there with the different sums? There would be 5 different ways, 5 different combinations of numbers that would give us 8.
I know, but like 2 and 6.
2 and 6, 2 and 6,
4 and 4, yeah.
3 and 5, 4 and 4, 6 and 2,
I think it's
the other way around. Because you have 2 different dice. Alright? So a 5 and a 3 is different than a 3 and a 5. So it counts as 2. Okay? Good question though.
And dice B.
What?
You have dice A and dice B.
Yes. You could think of it as die A and die B.
Yeah.
Alright? So now we have these, and basically you end up with 5 out of 36 times 5 out of 36 times 5 out of 36, which is just 5 out of 36 cubed, right? And what do we end up with if we do that?
1, 2, 5. It's over 46,666.
Okay? Is that what you guys got? Well, 125 over 46,550
Do we need to use
or 656?
Do we need to use one minuses?
Not in this case. Not in this case. Because here they're just asking us for getting an 8 3 times in a row.
Yes.
Okay?
We don't need one.
Now guys, we could use this as well for what's the probability of, say, rolling an 8 and then rolling, say, a 6. Well, let's not do 6. So let's do a 4.
Because they're both the same.
Because they're the same. Alright? So, the probability of 8 times the probability of 4.
5 over 36 times 3 over 36? Or times
Okay. 4 is 3 over 36, yeah. Which is helpful if we reduce maybe, okay? So we could reduce that to 1/12. And we have a 5 out of 432.
Yeah.
5 out of 432 chance of rolling an 8 and a 4 in 2 rolls.
Don't gamble, people.
Okay? Alright, does this make sense so far?
Yeah.
If you have independent events, you could just multiply the probabilities. Okay? Now, here we have another example. We say here that approximately 65% of the population of the U.S. was 25 years or older in 2004. In a survey, 10 people were chosen at random from the population. What's the probability that all 10 were 25 years old or older? Okay? Now here's a good rule of thumb. Okay? I know if we were talking about you guys and I said, okay, what's the probability, of picking someone that's older than 17 years old? Okay? Then if I take one of you out of here, since there's only 13 of you to begin with, our probabilities are going to change a lot, right? On my next person I pick.
Yes.
Right? So would that be an independent situation?
No.
No, because the probabilities are changing. If I'm dealing with the population of the United States, somewhere around what, 330 million people?
So we assume that not changing.
Yeah, we would assume it doesn't change, because when you take one person out of over 300 million people,
Doesn't change a lot.
your probabilities are not going to change. At least not to the point where it's going to matter. Okay? So if you see a large population, we're going to assume independence. Okay? So in this case, I'm picking a person. What's the probability that first person I pick is 25 years old or older?
65%.
Yeah, it's 65%, alright? What's the probability the next person I pick is 25 years old or older?
65% as well.
Okay, and how about the next one? Yeah, so if I do this 10 times, how could I rewrite that?
0.65 to the 10th power.
There we go, 0.65 to the 10th power. That's going to give us the probability of picking 10 random people and having all of them be 25 years old or older. Okay? Now, that's easy. Also, getting the probability that none of them are 25 years old or older would be pretty easy as well. What would that be?
1.35 to the 10.
Yeah, what's the probability that they're not 25 years old or older? Here's that complement.
1 minus.
So yeah, 1 minus 65% would be 35%. Okay, so the probability of getting all 10 less than 25 years old is going to be 0.35 to the 10th. So guys, when we're dealing with all of them or none of them, it's actually really easy to do. Okay? The challenge comes though when we say what's the probability of getting 8 of them to be 25 years old or older? Okay? Let's think this through. Okay? The probability was 65%, right?
Yeah.
Alright. So I want 8 of them to be 25 years old or older, right?
And then 0.65 to the 8th.
Okay, so 0.65 to the 8th. Okay? But that means how many people do I have who are not?
2.
That means I have 2, so how would I account for those guys?
35 to squared.
Yeah, 0.35 squared. So I have 8 people who are older and 2 who are younger. However, if I'm picking 10 people and 8 of them are 25 years old or older, how many different combinations could I have of those 10 people?
8 factorial?
Okay.
10 people or 8 people?
The 10 people.
Oh.
Like I could pick all 8 of them, my first 8, or I could have all 8 of them be numbers 3 through 10, or I could have, it was the 8th and 9th one that were not. Okay? So I have to account for all those different combinations of older people with the 2 younger people. So how would I figure that out?
Oh, wouldn't you take 0.65 to the 8 factorial? And I'm winging it.
No, you're thinking though. Think about what we've done in the past already. 10 choose 8, okay? Or 10 choose 2. It actually doesn't matter either way. Okay? But if I had 10 choose 8, what does this look an awful lot like?
I don't know.
Yeah. You remember the binomial theorem?
Yeah.
Okay? Well, this is an application, the binomial probability theorem. Okay? Now, I don't need the binomial probability theorem if I'm figuring out if all of them work, if all of them are what I'm looking for, or if none of them are. But if I have any kind of a combination, I would have to use this. Now, notice here the rules for when you can use the binomial probability theorem. First of all, you want a repeated event, okay? A repeated event. Remember the binomial theorem, we had a plus b to the n, right? Or x plus y to the n, or whatever. Okay? The repeated part comes with this exponent. Okay?
So in this equation, what would be in the 0.65 and the 0.35 would be the exponent?
Well, this actually would be one specific term from the expansion of, how many people were we picking?
10.
10. So something to the 10th power. Alright? The number of times you're repeating, and I know repeating may not seem like it makes sense here, but you're picking a person, you're picking another person, you're picking another person, you're picking another person. You're doing that 10 times. Okay? So you're repeating that decision to pick a random person. Okay? Another thing is that each of those events must be independent. Okay? If the probabilities are changing, you cannot use binomial probability. And then we have the next critical aspect of this, is that this only works when you're considering things that only have two possible outcomes. Alright? Here, we had someone who was 25 years old and older, or we had someone who was not. And when you hear this, you should be thinking they have to be complements of each other. Okay? So the expansion that we're working with here is 0.65 plus 0.35 to the 10th power. Okay? There's the binomial we're expanding. The probability that they are greater than or equal to 25 years old, and the probability that they were less than 25. They have to be complements of each other. Okay? Yes?
Is there going to be a formula sheet? Not on the quiz, I mean like in the folder?
Not, I don't think so. I know I have a handout, and there's a couple of days of just practicing later so we can get them all down. But this you're going to use so much you won't even need, you don't need a formula for it.
Yeah, no, this is like
So.
repeat.
Yeah, oh, and that's the nice thing about this, guys. Once you see how this is working, it's actually even a little bit easier than, hey, find the term that has x to the 4th in it, or find the 8th term. Here it's going to be, what's the probability of getting 8 people of a certain age? Okay, so that has to be 8, to the 8th power. Okay. So, the binomial probability theorem, repeated independent events with only 2 possible outcomes. Notice the terms in the expansion will give us the probability of different outcomes. Okay, 8 and 2 people from each group. We could have done, 5 and 5, or what's the probability of getting only 1 person older and 9 of the other. Every term in that expansion is going to give us a different outcome. Okay? Notice though, what will this whole expansion add up to?
The probability?
Yeah. What?
100.
100%. Because look, what's 0.65 plus 0.35? 1. 1 to any power equals 1. Okay? So, if I just said expand this, that'd be easy, you just put 1, okay? Because every time we do the binomial probability theorem, it'll expand out to total 1. That's why we don't bother, okay?
So what about like 10 choose 8, like that whole, it's just going to be 1, right?
This right here, let's figure out what this equals, okay? 10 choose 8.
45.
Yes, 45. Times 0.65 to the 8th times 0.35 squared. What does this all equal? Come on, you guys have your calculators. What did I tell you? Get your calculators out if you don't have them out yet.
Right, well, 0.65 to the 8th is 0.03.
Alright, so if we figure that out, we would end up with 17.6%. That's our chances of getting exactly 8 older people and 2 younger people. Okay? What are you trying to do? Alright, so just to kind of sum things up here, alright? Let's say that E is some repeated independent event. Okay? E. Alright? So, one way of summarizing this is we let P be the probability of E. Q is the probability of the complement, or not E. So that's 1 minus P. N is the number of times we're repeating this experiment. Okay? So we're going to consider terms of this expansion, the P plus Q to the N. Alright? So that's just kind of a summary of what we were just talking about. So let's practice this with a couple of examples. Okay? Suppose that the methods used by shoppers to pay for merchandise are as shown in the circle graph. 2 shoppers are chosen at random. What is the probability that both shoppers paid for their purchases only in cash? Okay? Now, it's asking for both shoppers. Do we need to use the binomial probability theorem?
No.
Why not?
Oh, it's not repeated?
Well, it is repeated. We have 2 different shoppers, right?
Not independent?
With different probabilities?
No, they have the same probability.
It's the same probability.
What's the cash?
32%, right?
Yeah.
Only in cash. Ooh.
Both shoppers?
So the probability of paying in cash is what?
8 over 25.
Okay, yeah, you could, or just 0.32. All right. Why don't we need the binomial probability theorem in this case?
Because we don't choose the 2 people from the 7. We just choose randomly.
We always have to pick randomly, so that's not why. Yep.
You're only choosing from one probability. You're not comparing it to the rest of the probabilities. You're only using 32 out of 100, not going 32 out of 100 plus, let's say 7 out of 100.
Well, that's the thing. We could do binomial probability with either of those, okay?
Because
Notice what it's asking. It's what's the probability that both. Remember what we said at the beginning. If you're getting both, if you're getting all of them doing the same thing, either all of them are or all of them are not, then you don't have to use the binomial probability. It would just be the probability to that power, right? Okay? So it would be, if we have 2 shoppers and we want both shoppers to pay in cash, what's the probability?
0.32 squared.
That's right, okay? What's the probability that both use cash? It's 0.32 times 0.32, or 0.32 squared. Okay?
1.1024.
Okay? So approximately 10.2%. Do you understand what we did here? So that's the main idea, what we're doing. Okay. Another one. Okay. Flexible work hours. In a survey, people were asked, okay, Notice here, if we have a survey or something like that, we can assume independence because we're assuming it's a bigger population, all right? So we're assuming independence here. In a survey, people were asked if they would prefer to work flexible hours, even if it meant slower career advancement. In other words, if you could work, kind of make your own schedule up, would you prefer that, even if it meant that you wouldn't advance in your career as fast? Okay? The results of the survey are shown in the circle graph. 3 people from the survey are chosen at random. What is the probability that all 3 people would prefer flexible work hours?
You don't need binomial.
0.78 divided by 0.7.
To the third.
To the first.
Hang it.
Yeah, to the first.
To the third, okay? So the probability that someone wanted flexible hours, probability of flexible hours was 0.78. Again, we have all 3, so we don't need the binomial probability theorem. So it's simply
47.5%.
0.78 to the third power. And what'd you get?
47.5%.
Okay. All right.
So if it's asking for like, what are you pick 3 people, what are the chances you get 1 flexible hours and 2 rigid hours? Then you'd use the binomial.
Yes.
Okay.
Yes. Okay. All right, let's try one more here. We have a fire company. We have 2 rescue vehicles to serve the community based on demand of the vehicles and the chance of mechanical failure. The probability that a specific vehicle is available when needed is 90%. The availability of one vehicle is independent of the other. Find the probability that both are available, neither is available, or at least one is available. Okay? Try this one on your own here. I'll give you a couple minutes. So, someone talk us through part A. Who wants to volunteer to talk us through part A? How would we do this one? Donald? You want to do A?
Okay. Part A. Suppose there's one, variable. So there should be 0.9 squared.
Good. It's a both one, so we don't have to go through the whole theorem, right? It's just 0.9 squared. So we'd have an 81% chance of both of them being available. Okay? All right. Who wants to tell us how to do part B? Ben?
So for B, you would just do the probability of 1 not being able to do it, which would be the probability of 0.10
Okay.
squared.
Good. All right. So here we have a neither. So that's 0.1 squared, so 0.01. Right? All right. So then C, what's the probability that at least one is available? Neve?
You do 1 minus 0.01, which gives you 90.99.
Good. 0.99. All right. So 99% of the time, at least one of the 2 engines will be available.
That's good to know.
Okay?
Wait, why don't we do the...
How did you do it?
I did the 2 choose 1 times 0.81 times 0.01.
Times 0.9 times 0.1.
Yeah.
Okay. that works, okay? Because here we want one to be available and one not to be available, okay? And then there's two different ways that could happen with the two different vehicles. So that would be, if we do that, that's 0.09 times 2, so that would be 0.18, but that's exactly 1. It could also be both. So what do?
You have to add the both.
Okay, good. So we had the both, which we already figured out on part A, was 0.9 squared. So 0.81 plus 0.18, we get that 0.99. So either way works.
So I just did the harder way.
You did it harder way, but you definitely want to do it in this case it didn't make a huge difference. You definitely want to use the complement though. If say we had 10 rescue vehicles, what's the probability at least one would be available? Because you don't want to have to do 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 and add all those up. When you could just do 1 minus the probability of none of them being available. Okay?
Wait, why don't we do that for 55?